Hi everyone, today I'm presenting my work, Jaywalking Index, Visual and Sociodemographic Patterns in London. In the early 20th century, people used to cross streets at any location, so jaywalking, which means crossing a street outside of a crosswalk, was a very common practice because pedestrians were expected to cross the streets freely. Even after the demarcation of crosswalks, pedestrians never stopped jaywalking. And it is important to know that jaywalking, despite a risky behavior, is not illegal in the UK. Currently, the high rate of accidents on Oxford Street can be explained by the competition for space between pedestrians and vehicles. So, to shift from car dependency to more sustainable modes of transport, London has set targets to promote walking as a primary mode of transportation. So, by the end of 2024, the aim is to increase the number of walking trips by over 1 million per day, with a further goal of 80% of all journeys being made on foot, by bicycle, or using public transport by 2041. However, some challenges hinder pedestrian mobility, as Londoners are most concerned about the lack of pedestrian-friendly streets, the prevalence of road danger, and the fear of getting to road accidents. So in order to address these concerns, the city adopted the Vision Zero in 2018, aiming that no one is killed in or by a London bus by 2030 and to eliminate all deaths and serious injuries resulting from road collisions by 2041. The Vision Zero Action Plan also identifies human error as the leading cause of about 90% of all collisions in London. And key strategies of the plan include reducing speed, targeting dangerous vehicles, protecting vulnerable road users, and improving street design. However, one significant gap in the Visual Zero plan is the absence of detailed information about pedestrian characteristics and behavior, especially in the specific cultural context of London. So my research question is, how can understanding the social demographic characteristics of jaywalkers and the urban context surrounding jaywalking incidents contribute to improving pedestrian safety and reclaiming streets over cars? The first hypothesis is that the social demographic profile of jaywalkers in London can facilitate the development of more targeted public policies for specific social groups. And the second hypothesis is that a jaywalking index based on computer vision and the landscape could predict the likelihood of jaywalking incidents across London, facilitating the identification of precise locations for urban design interventions. Classic urbanism authors like Kevin Lin, Jane Jacobs, and Ingel provide valuable insights into how the visual aspects of the streetscape influences people's behavior in public spaces. Other factors influencing jaywalking behavior have also been explored and comprise social demographic characteristics, perception of crosswalks, confidence in being seen by a driver, and inadequate streetscape design. Recent research has used artificial intelligence, including deep learning techniques, pre-trained object detection models, and machine learning combined with image processing. However, these methods were developed for real-time jaywalking detection, lacking static jaywalking detection. Regarding the methods, 4 core steps were taken to comprehensively investigate jaywalking crashes and urban design elements. First, the most recent accident data was collected from Transport for London in January 2024 and covers the period from January 2018 to June 2023. So this period covers the phases before, during, and after the pandemic, as well as the time frame in which Vision Zero measures are implemented. The data was filtered and cleaned to include only crashes involving pedestrians, resulting in a total of 25,732 crashes. In London, various positions are employed to geocode accidents. Some of these positions include crosswalk, the zigzag app, up to 50 meters from a crosswalk and not on a crosswalk. In this context, the Transport for London classified the crashes in 10 categories, covering a wide range of positions. However, more than one category referred to jaywalkers, such as categories 2 through 6. Therefore, the original categories were adapted as Class 1, which are the accidents on crosswalks, and Class 2, which are the accidents resulting from jaywalking. The other typologies that are neither on crosswalk nor jaywalking were disregarded. So to analyze the environment around crashes that happen due to jaywalking, the Google Street View imagery was used because it replicates a very similar view that a jaywalker sees while jaywalking. To collect GSV images, a street network for the entire London was downloaded from OpenStreetMaps, and GPS points were placed randomly every 50 meters along the defined street network. So with a list of lat and long pairs, the metadata was requested for the location using the GSV image API. And at each point, 4 images representing all directions of the visual field were collected at 0, 90, 180, and 270 degree, totalizing 280,000 images. And each of the 4 images at each point form a panorama. After collecting the data, some steps were taken to guide the analysis. First, the geolocated accidents dataset was important to QGIS for initial analysis. Next, a buffer of 60 meters was created around each accident point. So this is the minimum distance recommended for a signalized crosswalk and an accepted distance for clear observation of objects. After buffering, the GSV dataset was imported to QGIS, and for detailed analysis was separated into images in locations with accidents and without accidents. Simultaneously, a Python algorithm was employed to segment the images and quantify the elements of the landscape surrounding the accidents. So during the semantic image segmentation, a GPT model previously trained on the 8020K dataset was implemented. So this model classifies the pixels according to categories. For each image, these categories receive these scores based on the proportion of pixels within the category. The ADE20K dataset originally has 115 segmentation categories, but in this research, they were reduced to the 15 most relevant for the analysis according to the literature. The analysis and results were divided into 2 categories, which are the socio-demographic characteristics and the image segmentation statistics. The results regarding the total number of accidents align with other similar mobility patterns for the same period, and this could be attributed to the pandemic. And while the data for 2023 remains incomplete, early projections indicate a number similar to that of 2022. So regarding the spatial distribution of the data, although there's a noticeable concentration of incidents in the city center, it's also crucial to recognize that crashes occur throughout the entire city. It was also found that the average distance of pedestrian accidents from the nearest intersection is around 16 meters, suggesting that a significant portion of pedestrian accidents occur close to intersections, where traffic flow and pedestrian movement intersect. It is also important to know the proximity of accidents involving pedestrians who cross outside designated crosswalks to actual crosswalks. With an average distance of 4.3 meters from a crosswalk or 70 meters from an intersection, it indicates that many accidents involving jaywalking pedestrians occur remarkably close to safer crossing points. The proportion of male and female victims has remained relatively balanced over the period and corresponds to what was found in the literature. The severity of accidents follows the same pattern as the overall number of accidents. However, while there was a notable reduction in the overall number of accidents, the severity of those accidents underwent a small, albeit crescent change. One might explain this pattern is the reduced vehicular traffic during the pandemic's early stages, so roads may have become more conducive to higher speeds, increasing the likelihood of serious accidents. Regarding age groups, 11 age brackets from 0 to 99 years were considered for classification. The age groups with the highest number of victims were the 20-29 and 30-39 years old group, respectively. So they correspond to 35% of all accidents. However, upon closer examination comparing the accident data by age group with the age pyramid of London, there is a reversal in the population to accident ratio in the age groups of 20-29 and 30-39, indicating that the 20-29 group may exhibit more risky behavior. As for the 5-14 and 15-19 age groups, the proportion of accident is higher than the proportion of population, highlighting that these groups are more vulnerable to accidents. In terms of position, 35% of crashes occur due to pedestrian crossing outside crosswalks, with another 24% happening within crosswalks. This highlights the need to focus on both pedestrian and driver behaviors to improve road safety. In terms of analyzing accidents by class, the volume of accidents due to jaywalking is double the volume of accidents on crosswalk. And in terms of spatial distribution, it's notable that in both cases, there is a distribution throughout the entire city and a greater concentration in the central zone, similar to the previous spatial results. Regarding the total number of accidents per class, there is a downward trend in accidents occurring due to jaywalking, while there is an upward trend in those occurring on crosswalks. This pattern suggests a potential shift in pedestrian behavior towards safer crossing practices within designated areas. However, it is important to acknowledge uncertainty regarding whether this reduction in jaywalking is due to intentional changes in pedestrian behavior or potentially increasing distraction and risky behavior among drivers. So further research and analysis are necessary to disentangle these factors. By analyzing the age groups by class, although the predominance is among the age range of 20 to 39 years, there is a higher proportion of accidents happening on crosswalks for these groups. On the other hand, there is a higher proportion of kids aged 3 to 12 years old being hit by vehicles while jaywalking, highlighting the vulnerability of children to traffic accidents. Regarding gender, unlike the general analysis where the majority of victims are consistently male, the number of female victims is higher for accidents within the crosswalk, suggesting a potential difference in risk exposure or behavior patterns between genders within the context of pedestrian accidents. Concerning the severity of accidents, in addition to there being more than double the number of accidents outside the crosswalk, the severity of accidents and the fatality rate in the jaywalking group are slightly higher. So the results of the image segmentation were divided into three sections, which are the statistics of the variables, the landscape analysis, and the logistic regression. When analyzing the spatial distribution of these variables, two distinct groups emerge. The first comprises variables with high concentration in specific areas of the city, such as building, sky, grass, house, person, and bicycle, while the rest of the variables have a more uniform distribution throughout the city. Variables such as road, sky, building, tree, sidewalk, and car exhibited a more homogeneous distribution with higher values and few outliers, highlighting a higher proportion and frequency of these elements in the urban landscape. Conversely, wall, grass, person, house, fence, signboard, street light, bicycle, and traffic light showed a concentration of lower values, with a large number of outliers. This suggests that these elements generally have a lower proportion in the landscape, but in many cases, their proportion increases significantly. Although the results may indicate variation in data due to the angle of the images and the distance of the camera from these elements, it is noteworthy that the human field of view is very similar to that of the photos. Therefore, we also perceive these elements in relation to the distance in which we are from them. Therefore, when evaluating the statistical and spatial distribution of the data, it is observed that the use of computer vision brings satisfactory results in quantifying urban scenarios based solely on image segmentation, offering meaningful results. After analyzing the variables as a whole, the data from the variables were divided into 4 groups corresponding to the 4 accident positions on crossing zigzag area 50 meters from crosswalk and not on crosswalk. The objective would be to identify any changes in the landscape among these positions. Overall, the means of the variables were found to be very similar, with variations around 1%, indicating no significant statistical difference. This means, as expected, that the landscape around these different groups of crashes tends to be very similar due to spatial proximity. So in order to build a logistic regression model and compare how the changes in landscape are correlated with the likelihood of being a successful jaywalker, a sample was created containing 4,000 GSV points within the 60-meter buffer where jaywalkers experience crashes, and 4,000 GSV points outside the buffer in areas without any accidents. So the points were selected randomly and are distributed throughout the city. So in total, we have 32,000 images corresponding to the 8,000 GSV points used for the logistic regression. After that, I was able to analyze the scenarios by understanding the composition of landscapes seen by a jaywalker while jaywalking, understanding the proportions of pixels for each variable in every image. So this allowed me to create a logistic regression model to determine the weights of each variable in scenarios with jaywalking crashes and those without any crashes. So the jaywalking index is essentially an equation representing how the independent variables, shown in black, affects the dependent variable, shown in blue. In other words, each variable has a weight that impacts on the probability of being hit by a vehicle while jaywalking, depending on where they are jaywalking. And each of the variables in the equation must be filled with the scores found in the image segmentation results. These are a few examples of the landscape with some probabilities of being hit by a vehicle while jaywalking using real images. The first seems to be more vibrant in terms of urban activities with a probability of around 6%, while the third seems to be a low density residential area, less likely to experience a jaywalking crash with a probability of less than 1%. So by understanding the environmental factors that contribute to jaywalking, we can design safer, more pedestrian-friendly cities. So this index can be useful to help planners and designers prioritize some places for urban design interventions and reduce pedestrian crashes, especially in developing countries where the budget is often limited and require more assertive analysis. Furthermore, when applied to another city, this method adapts to the cultural nuances of that area, as pedestrian behavior varies in significance across different cities, impacting the results. So my final message is that it is important not to discourage jaywalking, but to adapt our cities to become more pedestrian friendly, thereby helping pedestrians reclaim the streets from cars. Thank you very much.